So in the last video, I alluded to a kind of secondary method that we may have for calculating these volumes of revolution. And you may remember that one of the first examples that we worked on in the last one was we had a parabola. We had y is equal to x squared. I stretched it out just a little bit just for the sake of having some more room to illustrate. And we were trying to find the volume of the shape that we got, rotating. Let's just say this is 4. Rotating this particular slice here around the x-axis. Okay, and so the premise of this video is we're going to start with the same exact idea, and we're going to remember that if we want total volume, right? Total volume is what we get when we add up a whole bunch of tiny volumes. But the thing that's going to be a little bit different this time is, unlike the last video where, we were maybe taking X and making these tall vertical slices and making these discs around, right? Or sometimes washers, kind of depending on our shape. We also learned that we don't just have to take our slices straight up and down, and that sometimes there are reasons why we may want to take horizontal slices. So we're going to try that for this problem and just kind of see what happens. Excuse me. Okay, so if in this particular example, right, we first get this point, which I'm giving you x is equal to 4, so we're going to know this is the point 4, 16. If you paid attention in the last video, then we kind of identified that this is going to be our interval right here. We're going to take a random y value. We're going to make a horizontal rectangle right here. And we would make a whole bunch of them for every single y value in this interval from 0 to 16. Now, the only thing that's going to be different is that when I take this slice and I rotate it around the x-axis, I no longer get a disc or even a washer, right? We're going to get whatever the name of this particular shape is. And hopefully, we've spent enough time playing with our Legos that we know that this particular shape right here is a cylinder. And so in this formula, these tiny volumes that we're adding up, right? So we know, right, that we're going to have an integral, and these tiny volumes, again, is surface area, right? Surface area times thickness. But now we're talking about what surface area? Well, we're talking about the surface area of this particular cylinder, right? This is now the shape that we have to deal with. It's a hollow cylinder, right? It's not filled in. We're just scraping out kind of like a sheet of paper or a paper towel roll or whatever it is you want to think about. It's just a nice little cylinder shape. And so, just like before, we need to answer two questions. We need to answer what is the surface area of this cylinder, and so particularly this is a cylinder, and what is the thickness of this cylinder, okay? The second one's actually much easier to answer because like I said, this cylinder is hollow, but the walls of this cylinder do indeed have some sort of thickness, and that thickness is still given by, in this case, dy. So the thickness of this cylinder is dy, and all we need to do is to figure out the surface area of the cylinder. Now, if you were to go onto Google and look up what the surface area of a cylinder is, you would find the following equation, that it's 2 pi RH plus 2 pi r squared. And you may be wondering, okay, well, this is a cool formula, but do I need all of this? Do I just copy this blindly? And this is where we really need to be, good students and think about what each of these things are. Specifically, what is pi r squared? Well, pi r squared is the area of one of these sides, right? And why are there two of them? Because last time I checked, a cylinder also has a bottom. It's the area of the bottom side. But we're not talking about figuring out the volume of of this hollow cylinder, right? We don't care about those sides. We're not caring about that. All we want is the surface area of the wall of this particular cylinder, and that's not this bit. So we're going to erase that out, and then we're just going to make sure that this bit here makes sense. And so I'm just going to draw this cylinder a little bit more upright for us. So just kind of a general cylinder right here. Okay, and you're gonna have to use your imagination for a second, right? That a cylinder has a height, that it has some sort of radius, okay? But you need to imagine, right, like where does the 2 pi RH come from? Obviously it's the only thing left over. It has to be the surface area of the cylinder, but where does it come from? Imagine you have a pair of scissors and you snip that cylinder and you're able to open it up and you unravel it, like so. Okay, you open it up and you unravel it like so. I could pull it taut, and it would make what shape? It's going to make a perfect rectangle like so. Where this side is H, and well, the last bit, right, would be to figure out what that side is, because once I know what that side is, I could figure out the area of this shape. But that side is the same exact thing as this entire top edge of the cylinder. And that top edge of the cylinder creates a circle, which, if you remember what the circumference of a circle represents, the circumference is the measure of the outside edge of a circle, and the formula for circumference is 2 pi r. So that's where this formula comes from, is the top of this cylinder, if we were to snip it and unfold it, would have length 2 pi r and h. And so that's basically going to give us the area of the side wall of this cylinder. Okay, now before I continue, and before we've come up with this little formula, and before I continue, I want to kind of give you a bit more of a visual aid of what's going on here, because the discs made a lot of sense, right? The discs, when we made these vertical strips, and we did a whole bunch of them. You imagine that there's a whole bunch of them kind of stacked right next to each other, right? And that they work together to create a solid object. And it's a little bit harder for people when they first learn about the cylinder method to kind of picture that. So here's a picture, and I'll try to help interpret this as best I can. Imagine that we have some function that is traced out here, right? This is my f of x. And it traps this particular region here, okay? And we rotate it around, let's say, an axis. So in this case, it looks like they did the y-axis, right? Something like this, okay? And it creates, this round shape, this round 3D shape. Matches the drawing just fine. So how can we use cylinders to get the volume? Well, as you may notice, in this particular example, wrapping around, if I take a vertical strip and I wrap it around the y-axis, this example is a little bit different than the one we're doing because it's going around a different axis, but every single slice that you make here makes this kind of hollow cylinder with a little bit of like a thick wall, if you will, right? And the more slices that you make, if I make another one, say right next to it, right at the next x value, and I draw that cylinder, it's going to it's going to nest really well outside the other one. And if I do another one, right, I'm going to get a smaller cylinder, or rather a shorter cylinder that's maybe a little bit wider once I wrap it around, etc., etc. It's going to create this particular shape. This is, what happens when you take any one particular any one particular slice, and you wrap it around one of the axes and you create these cylinders. They stack together and you will get the volume of this shape. Now, it's a little bit of a strange method, I'll give you that, but it works really, really well in the same idea. If you think of those Russian nesting dolls that all kind of fit inside of each other to create an almost solid object, that's exactly what we're doing here. So going back to our example where we're taking this region that's trapped underneath y equals x squared and wrapping it around the x-axis, we are taking this time, just for the sake of doing something a little different, we're taking horizontal slices, and we're trying to right now come up with the intuition for the formula for this thing. And we remembered that total volume is, what we get when we add up a whole bunch of tiny volumes. Tiny volumes are like surface area times thickness. And we said, okay, well, the surface area of the cylinder is just going to be the wall, which we now came up with the equation 2 pi RH. And so it turns out that our formula here in like this particular example we're working with would be the integral from y is equal to 0 to y is equal to 16 of 2 pi RH, because that's the surface area, times dy, which is our thickness. Now, this thing's almost ready to go, but it has two problems. The first of which is, actually, I guess two problems that all kind of combine into one big problem, which is R and H need to be in terms of what variable? They need to be in terms of y, because that dy there tells us we have made the decision to do all of this with respect to y. Our bounds are in respect to y, so our r and our h need to be with respect to y as well. So this is the tricky part of this method, which is we have to look at this cylinder and we got to answer two questions. So let's try and answer the first one. The first one we're going to answer is, what is r in terms of h? Or excuse me, in terms of h, in terms of y. So the center of our cylinder, in this case, because we are rotating it around the x-axis, the center of our axis, or the center of the cylinder, is just going to be the axis. So our radius here, that right there is our radius r. And you could draw it on that side. I could say that the radius is right here. I could say the radius is right here, right? You can draw it however you want. But if you kind of look at this thing, wherever it is that I decided to take my slice at, the y value from that point down to the x-axis acts as my radius for this cylinder. So in this particular case, my radius, r, is just equal to y. It's whatever y value that we happen to be at, right? It's whatever y value that I am taking this slice at. Okay, so the radius ended up being not too bad, so let's investigate the height. Now the height's a little more interesting, okay, because the height of this thing, and let's kind of erase a little bit of extra stuff just so that I don't have too much here to boggle our minds while we're thinking about this. The height is given by this piece right here. And so the last thing that we really need to do is to figure out what is the distance, or the length of this little tiny slice of a rectangle that we have come up with. And this we should be a little bit more familiar with from the stuff we've done last week in determining the heights of these rectangles. So for here, we're going to take this x value, which is x is equal to 4, and we're going to subtract it from whatever x value we happen to be at this particular point. So I'm going to, maybe I'll write this one in pink. I'll do this. So there's an x value associated with that one. And so I'm going to say that, that the length of this particular rectangle is going to be the second one, the further one, which is x is equal to 4, minus the x value that we get from the bottom point. But hopefully you recognize kind of what we need to do next based on the previous video, which is that we cannot have an x here. We need it in terms of y. And so we need to recognize, okay, well, thankfully, this x comes from the equation y is equal to x squared. So we can take the square root of both sides and get x is equal to plus or minus the square root of y. And just like in the last video, because we are dealing with the right side of this parabola where all of the x values are positive, we have to be talking about the positive square root of y is equal to x for over here. So our height ends up equaling 4 minus the square root of y. And so that is going to be our setup for this particular integral. If we want to do this integral, okay, where we are finding the volume of this, this shape that we get by rotating this shaded region around the x-axis, it's going to be an integral from 0 to 16. The 2 pi can go on the outside because it's just a scalar multiple, so we can pull it out. Our radius r is just equal to y. And then we have the height, which we came up with is 4 minus the square root of y. And then we have a dy at the very end. And so this would do it. Now, I know what you're thinking right now. You're thinking, look, Dylan, in the last video, we had this really nice method. Okay, we had this really nice method where we took all of these straight up and down slices, and we said that to get the total volume, we just added up all of these tiny little surface areas times thicknesses. We said the thickness was dx, and the surface area was just a surface of a circle, in this particular case, pi r squared. We said that the radius was just the y value, and then because it came from the parabola, y is equal to x squared, and our x bounds here only go from 0 to 4. So this integral is just the integral from 0 to 4. The pi can go on the outside. We have x squared dx. This one I just came up with way faster, and it seems like way less elbow grease. I can solve this much faster than this other one, where I'm going to have to multiply this y in here, and I'm going to have to multiply the y in there, and use the power, whole bunch of stuff. And I do agree with you, okay? I do agree that in this particular example that I'm showing you, I probably wouldn't really take horizontal slices either. I would probably use the straight up and down slices and make discs, because I personally think that discs are an easier method than using the cylindrical shell method, which is the method that you're learning about in this video. But exactly as I just said, we're trying to learn a secondary method because, as you're going to see, it isn't always the case that I can use straight up and down slices, or maybe just slices that would result in the disc or washer method. So to kind of prove that point, let's do another example, one where maybe we can't really skip everything so easily. And in this particular example, let's say we're going to rotate the region trapped by, say, y is equal to x minus 2 squared, and y is equal to 9 around the y-axis. Okay, and so again, we kind of got to go back into our playbook and remember what it means to have a parabola like this. Remember that shifts the parabola to the right 2 units, so this particular parabola is going to look something kind of like this. Okay, we have y is equal to 9, so that's something maybe up here. Okay, y is equal to 9, and let's label this one y is equal to x minus 2 quantity squared. And all we're going to do is we just want to set this up. So we have this particular shaded region that we're going to rotate around the y-axis, and it's going to create some 3D shape. Now, in the way that we learned in the last video, we may try and do this with horizontal slices and just try setting up an integral that says y goes from 0 to 9, because if I make the slice at y, I can see that the bottom of this parabola, right, the very last rectangle that I would have to draw is at y equals 0, and the top one would be at y is equal to 9 all the way up there. But it doesn't work because we run into the problem where both ends of this rectangle, the top and the bottom, lie on the same function. So when we start doing the whole, top of the rectangle minus the bottom, they're going to cancel out, and we're just going to end up with 0, and it doesn't work, or at least it requires a little bit of a workaround. So in this particular case, using the disc and washer method isn't really feasible for us. It's not impossible, but I'm trying to give you, some intuition as to when you might want to use an alternate method. And so for this one, it makes more sense that I might want to make my slices straight up and down, because my top function and my bottom function are now different, so I'm not going to have any issues when I'm trying to answer the question of how tall is this rectangle. And so again, I'm going to make a little sketch, right, just a brief one, something that kind of indicates that, right, what shape I'm going to get to kind of help keep me on my toes about this whole process. So we're going to say that the total area, again, I'm going to start shortcutting a little bit, is going to be the surface area. Surface area times thickness, And we're going to do this for all of our rectangles that we can draw. Now, because we are doing straight up and down, we're going to need a couple things. We're going to need to know what that particular point is and that particular point is, because they're going to correspond to some x1 and x2 bounds that we have down here. And then furthermore, this particular rectangle that we've drawn is happening at some x value, and we need to draw one for every single x value between, along this interval, because I need to do every single cylinder possible. So we're going to say that our bounds here are going to go from x1 to x2, and we can solve those at a later point. To solve for the intersection, we'll plug in 9, we'll do a little algebra. In this case, we'll probably need to do a little bit of factoring. I'm imagining that these numbers aren't going to be super nice. And because, me working on algebra is not really the point of this video, it's working with this cylinder shell method, I'm just going to focus on coming up with the formula. So the thickness, based on the slices we've chosen again, here is dx, because that is as thick as that little slice is right there. Now the last bit is the surface area, and if we remember from the previous example, the surface area here is just given by 2 pi rh. And so the very last problem that we have to tackle is we need to get r in terms of x. We need to then get h in terms of x, and then we can actually go about solving this thing. So let's tackle the height first. So the height here is going to be the distance between the blue y value, if you will, minus, the bottom one is going to be the pink y value, right? That distance there is going to be the pink y value. And so, thankfully, I happen to know that this blue y value is just y is equal to 9. And the pink y value in terms of x is just going to be x minus 2 quantity squared. So there we go. There is the height of one of these cylinders, no problem. And now the question is, what's the radius? Well, again, what is the center of this cylinder? Where is it located at? The center is located just at the y-axis. That's the thing that we're rotating around. So when we're talking about, what is the distance from the center to this outside rectangle here, we're just talking about what is this distance right here. And if we are, where did we draw this rectangular slice at? We drew it at some x, and that x is exactly the distance that we are from the center. So that x is going to serve as our radius of this particular cylinder. And this is going to be our setup. So our final setup here is going to be our first x value to our second x value. I'm going to put the 2 pi on the inside. You don't have to. You can put it on the outside. We're going to have 2 pi times x. That's our radius. And then multiplied by 9 minus the x minus 2 quantity squared dx. And I do encourage you all to be mindful of your parentheses. Make sure that you are using them correctly. Don't accidentally distribute things incorrectly, because otherwise you will not get the correct answer. But yeah, so that's going to do it for this video. This one's a little shorter than the last one. I did an example of rotating something around the x-axis using the cylinder method. I did an example of rotating something around the y-axis with the cylinder method. And the last video in kind of like this 3-part mini-series is going to answer the question, how do I tackle coming up with the volume of something if I don't rotate it around the x-axis or the y-axis? What if I decided to rotate, this entire shaded region, right? Remember, we're rotating this entire shaded region around something, and we've only been doing the x and y axis, but what if I had said rotated around the axis where x is equal to -2, or what if I had said rotated around the axis where, x is equal to -2. This is y is equal to -2 down here. And what if I had said rotated around the axis where x is equal to 10 or something, right? How do we have to modify the things that we've learned in the first 2 videos in order to tackle rotating around just the non-standard axes? So that's what the last video in this week is going to cover. And when you think you've gotten the hang of this one, head on over to that one.